Here's your introduction to the EKG lab, and as usual we're going to go over the important terms first. The first term here is cardiac cycle, and that will be one complete cycle of contraction and relaxation. You will see on the EKG tracing, one of the big landmarks is the R wave, and so a lot of people measure the cardiac cycle from R to R wave, but I'll show you that. The electrocardiogram. So electro means electrical, cardio heart, gram to record. So we're recording the electric activity through the heart. And in case you were wondering, ECG, EKG, what is there any difference? There is no difference. I tend to say EKG because that's how I learned it, and the K comes from the German spelling for cardio. Of course, the English spelling for cardio is with a C, so then you get the ECG there for electrocardiogram. Either way, it's the same thing. Now, before we go into the EKG recording and what the waves look like and what they mean, I think we should review the conduction system through the heart. And so let me just kind of draw a heart. Let's see, Mother's Day is coming up, so hopefully I can do this nice big fat heart. Let's see, not too bad so far. Yeah, there we go. And so we're going to put the interventricular septum right here, and then we're going to put two atria on top of that. Let's just kind of make it looks a little goofy, but it's okay. Yeah, the left atrium shouldn't be bigger than the right atrium, so let me just kind of do it like this. Okay, so here let's label the chambers of the heart. Of course, we have the right ventricle right here, left ventricle right here, and then we have the left atrium and the right atrium right here. Okay, so where it all starts out, and let me just change to a different color. I added the superior vena cava and the inferior vena cava, and then also I just put in here this little spot in red. That is supposed to be the SA node. So the SA node, and this is the pacemaker of the heart. And the SA node depolarizes at a regular basis. The normal heart rhythm or the normal heart rate is about 70 beats per minute. So the SA node sends a signal about 70 times per minute. Once the SA node fires, and so the SA node is just a lump of cells that are right there at the juncture between the superior vena cava and the right atrium. Once the SA node fires, the signal will spread through both of the atria actually pretty quickly. Right here, and then it will end up going to the AV node. Now the AV node works kind of like a gatekeeper, or what you might want to picture is like a signaler on the freeway. You have this SA node signal spreading through both of the atria pretty quickly, and it's pretty broad right here, and then you're bundling everything up, and it's kind of a narrowing, so you want to hold up the signal. And the reason for the hold up is that you want to make sure that the atria have enough time to contract and put the maximum amount of blood into the ventricles, both of the ventricles. So you want to hold up the signal just a tad, and basically you are bundling everything up and narrowing it down, just like a signaler on the freeway if you're closing certain lanes and traffic's backed up and everything takes a little longer to get through. And that's kind of like the job of the AV node. So once we're at the AV node could technically function as a secondary pacemaker, but it's considered an ectopic pacemaker, so it's not a normal pacemaker, and the AV node can only generate a signal about 40 times per minute or so, so you would have bradycardia, actually abnormally slow heartbeat, if you just use the AV node. So the SA node is the normal pacemaker of the heart. Once the SA node fires, both of the atria will depolarize. The signal will then be bundled up and held up a little bit at the AV node before it starts spreading very quickly through the ventricles. And so we're going to start out with going down the bundle of His, which then splits off into two bundle branches. And then we're coming back up here using Purkinje fibers, which are extremely fast conducting fibers. So here, this is the bundle branches. And then here we have the AV bundle or bundle of his. And then once we are at the apex of the heart right here, then we're going to branch off into these Purkinje fibers. So that would be the last one right here, Purkinje fibers. I hope you can read this. Purkinje fibers. Okay. I think I'm going to delete this here and rewrite it. Okay. Just a sec. Okay, slightly better. But anyway, so now that you understand the conduction system of the heart, now we can see how that a recording of this electric activity as it goes through the heart, how that translates into a recording of the EKG. So let me switch color again. We're gonna start with the isoelectric line, so pretty much a straight line right here. And the first thing you're gonna see on a normal EKG tracing would be a P wave. I'm not sure why they're starting with P, but that's what it is. It's a small upward deflection on an EKG tracing. And the P wave represents the depolarization of the atria. I'm going to write that down later in a different color. So P wave first, and then we're going to have a little stretch of baseline again, and then we're going to go into the QRS complex. The QRS complex would be first a small dip down, that's the Q wave, a huge upward deflection, that's R, and then going all the way back down, that's S, and then we're coming back to baseline. So this would be QRS complex. It's not the prettiest Q, but QRS complex. And after a short stretch of baseline, we're going to go into the T wave, which is a fairly large upward deflection. So that's the T wave right here. Okay, so let me label in a different color what they mean actually. So here it is. The P wave represents atrial depolarization, and the QRS complex represents ventricular depolarization, and the T wave represents ventricular repolarization. Note the re here, and the other ones were depolarization. Okay. You might wonder if there's a ventricular D and repolarization. How about the atria? Don't they repolarize too? Well, it's true, they do repolarize as well, but the P wave by itself is already not that large. The repolarization wave of the atria is also not very large, and it's masked entirely by the massive electric activity of the QRS complex. So technically your repolarization wave would be sort of a little bump downward deflection like this right here, but you can't see it because the QRS complex basically takes over. So let's see on our checklist if we got everything. Isoelectric line, that is the baseline right here. The P wave is the small wave that represents the atrial depolarization. The QRS complex is this massive electric activity that represents basically the conduction from the AV node down to the apex of the heart back up toward the base, and all of this electric activity would be recorded as the QRS complex. And then the T wave is the repolarization of the ventricles. Now let's talk about interval versus segment. An interval is a stretch, is a portion of the EKG recording that includes a wave and a stretch of baseline. So interval, wave plus stretch of baseline, versus a segment that's just a stretch of baseline. So for example, right here, from the end of the P wave to the beginning of the QRS complex, that's just a little stretch of baseline. That would be the PQ segment. Okay, so interval is a stretch of baseline plus a wave, and a segment is just a little stretch of baseline. So we got these two. Bipolar limb bleeds, that would be the classic EKG tracing as measured with Einthoven's triangle, where you're going to have right to left arm, for example. It's basically a recording of the electric activity through the heart from various perspectives. And the classic EKG tracing uses three leads, bipolar limb bleeds, and that is known as Einthoven's triangle, where you are going to measure from right arm to left arm. You're measuring from right arm to left leg, and from left arm to right leg. So we'll go over this in a minute, but the Einthoven's triangle is this configuration of three leads, and they all are bipolar limb bleeds. So that means they're recording between plus and minus 2 poles. The augmented limb leads, they kind of go in between those classic leads, and they sort of give you another 3 additional perspectives. They are abbreviated as A for augmented, AVR, AVL, and AVF for right, left, and foot. Together, they would give you 6 leads on an EKG tracing, so 6 perspectives of looking at the electrical activity through the heart. The most often in hospitals, they will record a 12-lead EKG, where they then have another 6 chest leads for a more well-rounded picture of what's going on with the electric activity of the heart. Let's go through the terms here first. The heart rate, well, that's measured in beats per minute. So normal resting heart rate is about 70 beats per minute. And then, of course, if you exercise, you would go up depending on how hard you work out. The rule of thumb for the heart rate, for human heart rate, it's not unlimited for sure. The rule of thumb for human heart rate is 220 minus your age is the maximum heart rate you can achieve if you're working out or exercising at max capacity. So if you're 20 years old, you should be able to reach 220 minus 20 is 200 beats per minute is your max heart rate. If you are 100 years old and you're working out, then it's 220 minus 100, so then the max heart rate should be 120 beats per minute. Let's talk about some arrhythmias. Bradycardia is an abnormally slow heart rate. So if your heart is beating at 40 beats per minute, that would raise some concern unless you are an extreme endurance athlete, but you shouldn't have a heart rate that slow. So bradycardia is abnormally slow, but normal. It's a normal EKG tracing. Everything looks normal except that your heart rate is abnormally slow. Tachycardia is an abnormally fast heart rate. Typically, if your resting heart rate is over 100 beats per minute, that will be referred to as tachycardia. Atrioventricular block, or AV block. Let's go back to my conduction system up here. So here's the AV node, this one right here. And in the conduction system up here, you can see the AV node. That was the place where we were bundling up the signal, hold it back just a tad. If you have an AV node block, that means that the signal has an even harder time than usual to travel through this narrowed area, so this bundled up area. There are different degrees of AV node blocks. You can have a first, second, or third degree block, but basically it's the amount of signal that's allowed to pass through from the atria to the ventricles, and with the AV node being the gatekeeper basically. So if the gate is completely shut, that would be a complete heart block, so a third degree block. If you have various amounts of signal coming through, then you have either first or second degree heart block. So that would be the AV block. Flutter would be not a complete contraction, but it's more like a flutter. So you would have an attempt sort of to create waves, but it's just fluttering. And fibrillation is even more of a wiggle line. So that's when you have just a real wiggle line right there here. The mean electric axis of the heart, and let me take this off, this is not too pretty. The mean electric axis of the heart, that is sort of the main thrust of electric activity as it goes through the heart. Now if you picture the heart right here that I drew, you can tell that the mean electric axis would have to go down here, the interventricular septum pretty much following it. So in order to explain the mean electric axis, let me just draw Einthoven's triangle. We'll continue this on the next one.